Dear students, welcome to my channel. This is 7th video on part of speech tagging. In this video, maximum entropy model or MaxNet, which is based on the discriminative model, is discussed. This video covers theoretical concept as well as one sample problem on email spam detection by using the maximum entropy model is discussed. Let us start. Part of speech tagging problem. There are two approaches, either generate the data from class or class generates the data. Problem statement: data is available of the form D, C, where D is observation, that is nothing but words, and C is nothing but the hidden class. So here hidden class is nothing but our part of speech tag. Two types of model are there, generative model and discriminative model. In my previous video, that is part of speech tag 4, 5, 6, I discussed generative model in discuss, and the type of generative model, that is nothing but hidden Markov model, is discussed with the lot of problems. Now in this video I am going to cover discriminative model, and under discriminative category I am going to explain maximum entropy model. Now we will again see in detail the discriminative model. Data is there and we assume that hidden state is generated from the data, that is flow is upward, that is data identifies the class. For example, statements are given, that is nothing but data, and in that data either positive or negative class is hidden. By seeing the nature of data, we can assign the probability of that particular class. Examples are logistic regression, maximum entropy model, and conditional random field. Now in terms of part of speech tag, we have the words, and we can check that words, neighboring words and neighboring part of speech tag, that is nothing but we check the neighborhood area of the observed word, and based on that we determine the part of speech tag. That's why the flow is in upward direction. The goal is to determine the part of speech tag of the observed word. Various properties linked with the observed word are used, that is nothing but previous word, next word, previous part of speech tag, next part of speech tag. It includes both previous and future words as well as their tags. We determine the part of speech tag for the observed word based on its properties. The direction of the flow is upward. Now first we will see what are the limitations of HMM pause tagging and how it is overcome in maximum entropy model. Again there are limitations of maximum entropy model and they are overcome by conditional random field. The emission probabilities and state transition probabilities of the corpus are explicitly used in the HMM model. So we already seen that when we solve the problem of Viterbi decoding of HMM, at that time first step is to from the corpus first assign the part of speech tag, and after that create the emission probability matrix and state transition matrix. That is, it work with a data set that was labeled. That is, when we are giving the label, that is correct part of speech tag manually for the training data, that is means what we are making the database as labeled database. And once our database gets labeled, we can easily write down the emission and state transition matrix. But in real time it may happen that new words, for example specifically the proper noun, may comes which was not present in the corpus. At that time HMM creates a problem. So for that also one of the solution is Baum-Welch algorithm, which tackle the challenges of working the HMM pause tagging for unlabeled data set. For example, if new words comes into the statement, the EM algorithm, that is expectation maximization algorithm, which uses forward and backward approach to get the maximum likelihood estimate of the parameters of the hidden Markov model. So for example, if unknown word comes which was not present in the corpus, at that time we can take the help of EM algorithm, which is based on the forward and backward model of the hidden Markov model. Now we will see the issues of HMM. First is the unknown words. We might get some unknown words at the runtime that are not in the corpus. So in previous slide we already discussed that Baum-Welch algorithm is one of the solution for that. Then when the word was not present in the corpus, then that word has no emission probability. As a result, Viterbi decoding is not possible. We can use morphological signals to determine whether word is proper noun if the first character is capital. For example, if we are not getting the emission probability for that word, then we can use other clues. For example, if it is a proper noun, then its first character is capital. If the word has a suffix ed, then it could be past tense or past participle. Next is the limited context. In HMM model we use first order Markov model, that is nothing but bigram. that is we are using only one word previous history in Viterbi decoding. However, as seen in the example below, sometimes preceding background is not sufficient. For example, if the statement is passed and she passed, and we want to determine the part of speech tag for the pass word. Now pass is a verb, and when it is passed, it becomes past participle. When it is she passed, it becomes a past tense. Now here the hidden marker model will identify correctly, that is first past is a past participle, verb and past participle, and second past is a verb and past tense. But if we write down the statement like is absolutely past and she absolutely past, here in between is and past, she and past, that one adverb comes, and at that time it may difficult for the part of speech tag to determine the correct for the past verb. So solution is that don't use immediately only one word history, but we can go for more number of grams or higher order grams to determine the status for that particular observed word. So here if we use trigram, that is if we use a 2 word previous history, then this problem can be solved. Next is for big sentence, Viterbi decoding is slow, even it is efficient. Here we are using word features which are very much limited. So solution for HMM is use a feature rich classifier as a solution, and that is nothing but what? Maximum entropy model. It can be also called as max ENT. Here for example W4 is our observed word. Now when we want to determine the part of speech tag for W4, so at that time we are taking the help of the previous word, we are taking the help of the future words, they are nothing but features. Even we are taking the help of previous part of speech tag and the next tentative or predicted part of speech tag also. In exam generally the question comes maximum, write down short note on the maximum entropy model. So first next 3 slides are theoretical explanation, but it has that all the information that is required to solve the problem. Maximum entropy model, it may be represented by MEM or max ENT. For post disambiguation, HMM post tagging uses restricted features. Both the tag and the observed word in HMM are dependent on the previous tag. To establish the part of speech tag for observed word, the further features must be considered. A discriminative model is the maximum entropy model. It does the post tagging for a given sentence by combining several heterogeneous features in the probabilistic framework. Max ENT is based on the principle of maximum entropy. Now you will come to know how it chooses the maximum entropy features, which states that all of the models that match the training data, the one with the highest entropy should be chosen. When the conditional independence, this statement is very important, when the conditional independence of the features cannot be assumed, the maximum entropy classifier is used. Means here we are taking the assumption that whatever the words coming in a sentence, they are not independent, but they are depend on the previous and the future words and the part of speech tag also. So there is a conditional independence. This means that features are interdependent. This is especially evident in problems involving the text categorization, because maximum entropy model is a very popular and generalized model which is used for multiple applications. So because the characteristics of words and they are not independent. For example, if we want to make the text categorization, at that time we can't take the decision based on a single text, but we require to take the neighborhood information. Maximum entropy modeling is a machine learning framework. Classification is a problem of taking a single observation, extracting some useful features. Now single observation is nothing but our observed word whose part of speech tag has to be determined. Extracting some useful features describing the observation, and then classifying the observation into one of the set of discrete classes depending on these features. So now here our classes are nothing but whatever that part of speech tag classes. It is a probabilistic classifier. It indicates that likelihood that observation belongs to that particular category. It is a non-sequential categorization. This is again a very important point. When it comes to text classification, we may need to evaluate whether or not email should be categorized as spam. We must assess whether a statement or document represents a favorable or negative attitude in sentiment analysis. A period character must be classified as a sentence boundary or not. So these are nothing but the applications where we can use this concept. Maximum entropy belongs to the family of classifier known as the exponential or log linear classifier. So here we are using the exponential function. Maximum entropy works by extracting some set of features from the input, combining them linearly, and then using the sum as exponent. Example here, tagging. A feature for tagging might be this word ends in ed or the previous word as a adverb. For example, that is a problem that when the statement is absolutely passed, she absolutely passed, at that time we are using the various features in the neighborhood of the word passed, and based on that we can take the decision. That's why a feature for tagging might be this word ends in ed or the previous word was adverb to determine the correct part of speech tag for the pass word. Now this is the formula for maximum entropy model. Probability of C given X. Now here C is nothing but our classes, that is nothing but the part of speech tag which we want to determine for the observed word, and X is nothing but our observed word. So probability of C given X is equal to 1 by Z. Now Z is normalizing constant and exponent of summation of I Wi Fi. Now this formula will not be clear on this slide, but next when I explain in detail with the example, this formula becomes very much, and it's very easy to calculate also, and this is very simple to understand also. Now we will first see the applications that where the maximum entropy is used. It is one of the classical machine learning tasks. Sentiment analysis, for example, product reviewers like dislike about the product. Preferences, who will the person who vote for based on the demographic, would they rather have Superman, Batman, or whatever that example that is of demographic classification. Then next is diagnosis. Then all that applications comes under the category of maximum entropy. Now we will see one problem of maximum entropy model, but we are not directly going to solve the problem of part of speech tag, but I will take simple example, and in the next video I will explain the example for NLP, that how we determine the part of speech tag for an observed word by using the maximum entropy model. Now this is the simplest example, and by using this example you will come to know that how to apply the formula directly in the NLP problem. Now example of spam, not spam email detection. So now when we want to determine whether the particular mail is spam or not spam, at that time that features need to be determined. So here I just randomly pick up the features. So this is only for illustration. So some of the features of the emails that might be useful to determine the spam or not spam. So what it indicates that we require to take the features of that particular email. Means, for example, in part of speech tag, the word whose part of speech tag is to be determined, we require to collect the characteristics of that words using the neighborhood information. Now features of the spam mail are look at who the email is addressed to, check from the email address, check the greeting, look at the subject of the email, your domain is forwarded to another domain, bad grammar and spelling, no phone number in the signature. So these are nothing but characteristics, and by just synthesizing the text we can determine whether these features are present or not. So features are basically binary in nature, either they present or not present. Now some of the features are more inclined towards the spam than the others. We can assign weight to each features depending on the priority. Weight vary from -1 to 1. Now this is the 7 features are there, and their weight is represented by W1 to W7. Now here weight is assigned, that weight for spam mail also and weight for non-spam mail also. Now here see, when the weights are positive, it indicates that they incline to the spam, and when weights are negative, they are inclined to the they are less inclined to the spam. I will repeat again the statement, which is very important. When weights are positive and they are close to 1, they are inclined to the spam, and when the weights are negative, they are not inclined to the spam. And similarly we can do for the not spam also. When the weights are positive, they are inclined to the not spam, and when they are negative, they are not inclined to the not spam. So these weights I have just randomly assigned the weights to just illustrate the problem of maximum entropy model. So here what we require to take the input, find out the features. After that we assign the weight for that features. So here we take one input, that is one email, 7 features are there, and our classes are 2, that is spam and not spam. Features are binary in nature, either they are present or absent. If f of x is equal to 1 or 0, where f is feature and x is email. Therefore we have feature function fix with weight wid for each mail, because we are finding the features. That feature may be present or may be absent, but when present we require to multiply with that particular weight factor. Now here you will come to know that formula that we have just seen in the previous slides. Using the following approach we can predict decision D, because D is our decision, spam, non-spam, for the given input X. The input X has n binary features, where n is our 7 binary features that are either 0 or 1. For step-by-step procedure, for each feature determine whether f of x is 1 or 0, check whether that feature is present or not present, multiply each feature by the weight associated with, that is WID, that is we require basically take the multiplication of the features with the weight. For n features, add the total f of ix into wi. We are taking basically summation. So this formula is very much easy, that is for I equal to 1 to n, fix into wid. Here feature is present, it comes 1, if it is absent it comes 0, and if it is present then only the multiplication with weight factor takes place, and we are taking the summation. Now here we have two classes, spam and non-spam. So we are calculating the this for two times, one for spam and one for non-spam. So takes the exponent of summation. So we are using the exponent operator here, and there is a reason to why to use exponent operator. I will explain it on the next slide. So numerator is equal to I equal to 1 f summation of fix into wid. So here for when two classes are there, we are getting two types of numerator, one for spam and one for non-spam. Divide the numerator by the sum of numerators for every possible decision t. So denominator is nothing but what? For example, in the numerator we consider only spam, and in denominator we consider the spam as well as non-spam. Second numerator is only for non-spam, and denominator is again spam and non-spam. So this is nothing but what? In the numerator we are taking for that particular class, and in denominator we are taking the summation over the classes, means whatever the available classes we are taking all that summation. So here this formula is modified to here. So probability of C given X, where here this denominator is represented by Z, which is nothing but normalized, and this is exponent, and this is nothing but numerator, that is we are multiplying features with the weight. That is nothing but the formula of maximum entropy model. For NLP, C is part of speech tag and X is observed word, and for email example, C is spam or non-spam, X is email input, and denominator is a normalizing constant. Now we will take example. So email as input X, D has two classes, spam and non-spam, and from that email we find out that only F4, F5, F6 features are present and rest of the features are absent. So when F4, F5, F6 features are present, we are just taking that weight, because when the feature is absent we are getting that 0 value. So 0 into weight, it does not make any change. So I have shown only the weights for which that particular features are present. Here we will calculate the two scores, one for spam and other for non-spam. Now this is the formula. Now why we use the exponential function? This is the same that we used in a logistic regression. Exponential function as a graph that gets very close to the x-axis as the graph extends to the left, as x becomes more negative, but never really touches to the x-axis. Means it never touches the x-axis. That's why we are using the logistic regression formula for the in the form of exponential function. Now here we will calculate for two. One is for spam. So spam, the features are F4, F5, F6 and having the value 0.6, 0.7 and 0.5. So in the numerator it will come exponent of 0.6 into 1, 0.7 into 1 and 0.5 into 1. Other features are absent, that's why we are not taking. And in the denominator it will take for the spam as well as it will take for the non-spam, because denominator is nothing but summation of all D classes. So here this is the summation of the spam and summation of non-spam. So this is nothing but the denominator. Calculation is very easy. Now here we are getting the exponents of 0.18, exponent 0.18 and exponent, and here when we calculate we are getting the value 0.75. Now what is this? This is a probability. Now this particular X email that is having this spam, the chances of 0.75. So first we calculate the score for spam. Now we will calculate the spam score for non-spam and we compare. Now the same formula, only probability of non-spam given x, and in the numerator it will comes to the non-spam mail, and here we are calculating the answer. And here, as we are using that exponential function, our answer is always positive. So here we are getting that 0.25. Now for that particular email we are getting the two scores. For spam the score is 0.75 and for non-spam is 0.25. So ultimately the mail is classified as a spam mail. So in this way maximum entropy use the features and does the classification task. Now in the part of speech tag, what we are doing, for example here the problem is because of that absolute word comes between the past. So for example when we want to determine the correct part of speech tag for the past word, at that time we are using the variety of type of features. So I just given the example that we can use this, for example 9 features. So we can use that past word previous part of speech tag, current part of speech tag, then after that previous part of speech tag. It's all depend on that how you are taking that. So it may be that it may be ti-2, maybe auxiliary verb, t of i-2, maybe third person. So we can take variety types of features and we can assign the weight and we can solve the problem. So in the next video I'm going to solve the problem of maximum entropy model for the part of speech tagging, in which we are assigning the variety type of features and after that we are determining the part of speech tag. So this is just example to illustrate that how we are going to solve in the next video. So that's all about the theoretical part of maximum entropy model, and these are the references for maximum entropy model. I hope you understood the video. Thank you.